As we've talked about with the Wiggers diagram, pressure and volume in the left ventricle are constantly changing. There's another way to look at it besides just looking at the Wiggers diagram, and we can do this through the use of pressure volume loops. Okay, and so we've got volume on the x-axis, and we've got pressure on the y-axis. Okay, and these pressure volume loops essentially look like this. Okay, and where these X's are mark the changes in phases of the cardiac cycle. Okay, and so we're just going to start here. So this is 1, 2, 3, and 4. Now it's really easy to identify which phase you are in based on what's going on with volume and what's going on with pressure. So with phase 1, so if you can tell, volume is increasing, but pressure staying relatively the same, maybe a little bit of increase. So we're going to say big change in volume and a small change in pressure. Okay, that lets us know that we're in the filling phase. So if we go to phase 2, so we're here. So notice there's no change in volume, but we have a massive change in pressure. Okay, so volume stays constant, but we have a big change in pressure. And so that lets us know we're in the isovolumic contraction phase. Okay, this is where the ventricle is building up pressure so that we can open up the door between the aortic valve, or open the aortic valve so that we can get blood out of the ventricle into the aorta. So then next we've got 3 here, and so that goes from here to here. And so just to be clear, we go this way. Okay, so notice that volume ultimately decreases, but pressure increases for a little bit and then it decreases. So here we have a decrease in volume, followed by an increase and then decrease in pressure. So this is ejection. Okay, the initial increase in pressure is due to the strong, forceful contraction of the ventricle, but ultimately, even though the contraction continues the entire time, volume, enough blood is left of the ventricle that volume starts to decrease. And then finally with 4, we come here. So notice volume is staying the same, but pressure is decreasing. So we have constant volume, large decrease in pressure. So we're in isovolumic relaxation. Okay, and that's how a standard pressure volume curve works. I can spell relaxation. Okay, but we can change what's going on during each of these phases, or we can change these pressures. And this has to do with preload and with afterload. And so I'm going to talk about preload first, and I'm going to highlight it with blue. So what we're going to do, remember, preload is just left ventricular volume. Okay, it's the pressure in the ventricle before contraction. Okay, and that is equivalent to left ventricular volume. All right, so if we increase preload, what's going to happen to this curve? So I want you to think for a minute. I'm going to pause the video. What's going to happen to left ventricular volume? Or how is this curve going to change if we increase left ventricular volume, or end diastolic volume? Okay. And so the answer is we take segment 2 and we shift it out to the right. Okay, so we're going to have a higher end diastolic volume, and then what happens is we're going to have a little bit stronger of a contraction during isovolumic contraction. We're going to generate more pressure so that we can then get back down to our end systolic volume. Okay, so if we increase preload, what happens is we increase end diastolic volume, but our end systolic volume stays constant. Okay, and if we increase end diastolic volume, but we decrease end systolic volume, or excuse me, but end systolic volume remains constant, what happens is our stroke volume increases. And the difference between these two segments, this is our stroke volume. Okay, so that's stroke volume if we have increased preload. This is stroke volume if we have typical preload. Okay, notice that the stroke volume is greater when we have high preload. All right, next, and the other one that we've got is afterload. So I'm going to try and write that here. It's going to get a little cluttered. So we've got afterload. Okay, remember that afterload is the pressure the heart has to contract against. Or in other words, it's aortic pressure. Okay, as aortic pressure increases, afterload increases, which means it's more difficult for the heart to generate enough pressure to get blood out of the ventricle. Okay, so again, I'm going to pause the video here. What's going to happen to this curve, to the pressure volume loop, if we increase afterload? All right, and so the answer is end systolic volume actually increases. So this leads to an end systolic volume that's greater. Okay, and so now what happens is we're going to have some curve that looks like this. Okay, so and I know that everything's overlapping, but we're going to have this curve that looks like this. And so end systolic volume increases, end diastolic volume is constant, and then what happens is that stroke volume actually decreases. We're not able to get as much blood out because we're spending more time generating enough pressure to open up that aortic valve. Now the reverse is also true. If we decrease afterload, this line will shift this way. And if we decrease preload, this blue line will also shift this way. And so we'll change end diastolic volume and stroke volume. Whereas with afterload, we're only affecting end systolic volume and stroke volume.